Right, I picked up this thermal imaging system on eBay Germany. This is for the this is actually for an Audi. There's quite a few of these automotive systems coming out now. The idea is you've got a sort of forward-facing thermal imaging camera that can pick out hazards like pedestrians and so on. Some of the later systems also got stuff like automatic recognition of people to highlight and project it onto a heads-up display. But this is a fairly old. I think it was about 2008-ish from the dates I've seen on it. Be interesting to take a look at. There's two main units. There's a processor unit here and the actual camera head. Obviously this has got to sort of face forward, so the mounting positions for this are very limited, so I want to get this as small as possible. There's a window on the front which is fairly easily exchangeable, so obviously this is potentially vulnerable to damage or stone chips and whatever, so this actually unclips quite easily. There's a window here. You see a lens underneath, and there's also a heater. You see a sort of heater made out of flex PCB, and that's almost certainly a thermistor there for temperature feedback. It's just got quite a neat little clip detail, so this just goes on and then just clicks into place. I believe these are actually manufactured by Fleur. They also seem to be branded Autoliv. Autoliv seems to specialise in things like airbags and automotive safety equipment, so I'm guessing it's probably a Fleur camera core that's been integrated by Autoliv. And so there's versions of these for Audi and BMW, there may be some others around, others now. There's obviously a few signs of corrosion and so on around here. This has been sort of sat under a car bonnet for a while. The connector is 2 pins which are clearly power, and then there's a 4-pin which I believe this uses an LVDS interface. I got part of the cabling. That's the plug that goes into the camera end, and the other end of that short cable had a male connector, but because the connector on the controller end also has a male end, there's also a female to female cable that goes in between these that I haven't got, and then there's a connector that goes into the rest of the car system, so that will be power, video out, probably CAN bus for control, and a few other odds and ends. Right, there's a bit of trick to getting this out without tearing that little flex that goes up to the front. Is a little bit vulnerable. If you just sort of pull the thing apart, then there's quite a good chance you'll damage that. The trick seems to be to get this top bit to come out with the lid. It comes apart. There's two connectors here. Right, this backboard is clearly sort of power supply and filtering. There's massive great common mode filter there, which is presumably on the power lines. There's another one there, presumably in the video. So obviously cars are fairly hostile electromagnetic environment, so there's sort of filtering all over the place. There's another little filter there. Inside the back there's a little bit of silica gel to pull off any moisture that's inside. Interesting, on the back of this module there's another fairly big connector, so maybe there's some variants that have got an extra board on here, or perhaps it's for test, but yeah, it seems quite an expensive thing to put on the board just for test purposes, so maybe there's different variants of this module. Perhaps there's another version that's got some extra functionality, so it'd be interesting to see whether that's actually got sort of interesting data signals on it, or whether it's just sort of power or something. But don't often see sort of, it's a fairly sort of chunky connector that's not actually used. This is the inside bit. This housing looks identical to some of the Fleur Tau camera core products. Obviously they've used the same some of the same castings on here. This was actually locked down. I've already unlocked it from there. So a bit of sense. So there's a shutter in front of it, the calibration. And this lens, actually, it's interesting. Obviously that front bit's almost certainly germanium, so it's opaque, but the back looks sort of yellow, so I wonder if there's actually a zinc solenoid element in the back, because that looks a bit transparent. It's got a very yellowish tinge, so I think maybe there's that back part is zinc solenoid. That's obviously the sensors in this part, and this is the processing board. There's Xilinx, Spartan FPGA. I'll take a closer look at that board in a minute. Right, here's the sensor and the calibration shutter. Looks like it's just a little motor that flicks that. It's very, very light. I'm guessing because this is an automotive thing, you don't want this calibration to take a great deal of time, so I imagine that probably moves quite quickly. There's some, it's very light, but there's some sort of stiffening ridges down it, so I'd imagine that's pretty quick. This sensor looks like the same one that they use in the FLIR i7 series, which is sort of previous generation. I have seen a picture of an Audi camera that uses the same type of sensor that they use in the FLIR E series, which is a much smaller package, much lower cost package. So this is clearly the previous generation. Obviously they're using the same sensors in automotive and also their thermal imaging handheld products, just because of the large cost of developing these. They want to get the maximum amount of usage out of the sensor design. In fact, it's probably the automotive market that's really driving the development of these sensors to get the cost down and the size down, and then the thermal imaging sort of instrument market is just a bit, a bit of extra sort of icing on the cake, because the automotive market is potentially very, very big. You can see it's got a sort of window on the front that seems to be soldered down. It's probably indium solder or some other low temperature solder, and there's just a plastic clip. It's holding the sensor in place. And here we've got the sensor. There is actually a teardown of this sensor online. There's a company that did a full teardown of the FLIR I series, and they actually took the sensor apart, so I'll link to that here. But that's clearly exactly the same sensor. There's two big pads there, which apparently are for firing the getter to get the last pieces of last amounts of air out of the vacuum package. Well, let's take a look at this board. Obviously the main thing here is the FPGA's Xilinx XA2S1200. I think the XA is the automotive version of the standard XC series devices. There's a 25p64 serial flash that will be holding the configuration data for the FPGA, 50 MHz clock. There's RAM chips, a 256 megabit RAM from Micron. Incidentally, Micron have actually got a lookup thing on their website. If you type this code in on the website, it'll actually tell you the full part number, because obviously some of the parts are too small to have a full part number on them. So they'll actually look it up. Unfortunately, given the part number, it doesn't give you a direct link to the data sheet. You've got to search for that separately, which is a bit dumb, but at least they give you the facility to look these codes up to figure out what these chips are. There's a 74HC132. I'm guessing that's probably just level shifting, or just doing some fairly simple stuff to interface to the sensor. Down here, the chip marked T272. I'm guessing that's probably dual op amp again, which is probably generating analog levels for the conversion on the sensor. Again, like the FLIR E4 sensor, that there's no AZD converter on here, so the AZD converter is obviously integrated onto the sensor itself. And down here there's a DS90C241. Now this is a serializer chip. These are quite commonly used. They're originally designed for linking LCD panels in laptops. This takes a 24-bit parallel data stream and converts it into a single serial stream. There's a number of reasons why you want to do that. One is to reduce the number of wires that you're sending the signal on. Also, it eliminates the issues of skew. If you've got a parallel bus, then if you sort of send it down a long cable, you can get skew between channels. But this is now pretty much universally used in LCDs. Most of the LCD controllers and panels have got this built in. But although this is designed for LCDs, these can actually be used for any application where you've got, say, a wide data stream. You want to send down a single pair, so they're quite handy chip for doing that. And the output's designed to be, they've designed the coding so there's no net DC, so that you can pass it through inductive and capacitive barriers. So it gives you quite a lot of flexibility as to how you get your data from A to B. And that's pretty much it. There's not really anything of any interest on the bottom side. It's just passives, decoupling. There's a little common mode filter on the that's the connector that goes out to the front window heater. So because that's outside the metal casing. They're just using that to filter any transients coming in or RF emissions going out via that, 'cause obviously that could act as a small antenna. And this back PCB is nothing on this back panel at all. As you said, sort of power, and you can tell just from the capacitors and inductors this is just going to be power, sort of a few various switch mode converters generating the various voltage levels that it needs. So a couple of filters, that's probably a transient suppressor diode. One other thing I noticed on this board, there is actually a CAN transceiver, so it looks like what they're doing, they're using 2 of these pins for the high speed data, and there's also a CAN interface which is for sort of management and monitoring or whatever. It's presumably implementing a CAN transceiver in the FPGA, and that's really it. So there's not really a great deal to this thing. Hopefully that might mean the interface is fairly straightforward. Let's have a look at that. Right, the control unit as you'd expect, it's basically one PCB in here. It's conformally coated as you expect for automotive devices. So this is not, there isn't a sealing gasket or anything on here, so you might expect a little bit of moisture. I mean, this probably isn't going to be in the engine compartment, but it's you've got this sort of fairly heavy conformal coating, which is pretty much standard for automotive stuff. Let's have a close look at this board. Not a great deal on the bottom. There's a few sort of power components, and this is a Freescale MT9S12XD processor. This is basically still dealing with all the CAN bus interfacing to the vehicle. This is sort of designed for CAN control applications, so that's clearly what that's doing. Now, one issue with this conformal coating, it makes laser marked chips really difficult to read. Sometimes you actually have to crack the coating off to be able to read it. Sometimes you get a bit of texture so you can actually read through it, but sometimes it's actually very difficult to read. So we've got this obviously rather expensive looking connector for the high speed data. I'm not sure what the actual clock rate on this is. The serializer chips accept an input clock of I think 5 to 35 megahertz, so because that's then being multiplied by 24 for the high speed data link, it could be running up to sort of 800 megahertz sort of region. They're designed to drive up to about 10 meters of cable, so some fairly high frequency stuff going on there. So that's the receiver, that's the 90S124, which is the receiver, the counterpart of that transmitter device. Incidentally, this is the sort of functionality you tend to now see built into FPGAs. Things like the Spartan 6 have got on board high-speed serializers, so I'd imagine later versions probably don't actually need these external chips and actually do it directly from the FPGA. There's a couple of unpopulated locations sort of on there, and there's a little BGA there. I'm not sure what that's for. This is another FPGA, it's the XA3S500 Xilinx. A couple of RAM chips next to it and a flash. Again, this flash is almost certainly going to be FPGA config, but probably also the RAM for the program storage for these. These are Texas Instruments TMS320DM642 processors. These are sort of high-speed DSPs specifically designed for video processing applications. There's 2 of them on this board. I guess it's hard to know what they're sort of doing between the 2. Right next to this one there's an ADV7179, which is a PAL NTSC video encoder. So this is clearly generating a video display for a heads-up display to actually show the driver. So this one's process is almost certainly generating the sort of the output video. Maybe this one's doing the recognition and input processing. Not a great deal else. Obviously there's all the usual power stuff, switching regulators and so on. So this is just clearly taking the high-speed LVDS data stream from the camera, doing all its processing, probably providing some user interfacing and other stuff, then converting it to video for the driver's display. Well, I've had a quick poke around this thing with the scope when it's been powered up. There's not really much going on. I suspect it needs some instructions down the CAN bus from the controller. All I found really, there's a 72 MHz signal going into the sensor, but there's nothing coming out, so I'm guessing there's maybe sort of an enable line or something. So that may need a bit more experimentation to try and find anything. There is the LVDS data stream is coming out, but there doesn't seem to be anything actually happening on it, so there's nothing coming out of the sensor, so there can't really be anything coming out further downstream. But I've sort of read online that various places these things do some sort of handshaking to enable them and get them up and running, but I'm wondering if, even if there's some sort of difficult handshaking to get the LVDS stream, it may, my guess is that it might be just a case of pulling an enable line high or low on the sensor connector to actually get raw sensor data out to process that separately, but I don't have much time at the moment to play around with it, so I'm going to have to leave that for another time. I just hooked this up to the processor board, and they do seem to be sort of talking to each other over the CAN bus, but still no signs of activity around the image sensor, so I'm guessing this thing probably needs to talk to the vehicle system before it sort of wakes everything up and gets everything going. And just a quick poke around this connector on the back, I just found a breakout board with the right sort of pin out. The other thing you can see, there's a 72 odd megahertz clock data stream that looks like it's chunks of 16 bits, which this data stream looks fairly similar to some of the stuff in some of the FLIR TAO documentation, but with no sign of any data. They'll say there's nothing happening on the sensor, so there's clearly an enable somewhere that's not being enabled to actually get this thing spitting out real data. No draw, I just tried pulling a few pins down just in case there's any obvious test modes or anything on this connector, but nothing obvious. When it gets up I might just sort of try throwing a bit of CAN stuff at it and see what happens, but a bit busy for that at the moment, so I think this will have to go onto the toys to play with when I've got more time shelf for the moment.